So in this point, in this particular equation, this is our equation. So the equation or the system problem said that draw the phase trajectory of x1 is equivalent to x1 dot is equivalent to x2, and x2 dot is equivalent to minus 2x1 minus x1 square minus 0.5 x2. So this is the nonlinear equation. So for this particular system, we are requested to draw the phase trajectory of a system. So the phase trajectory makes the system stable or not. So here we have two things. So the first thing is we have to identify our system is stable or not. This is the first thing. The second point in here is drawing a phase portrait diagram. Phase portrait diagram for this stable or non-stable or unstable system. For drawing phase portrait diagram or plot phase portrait diagram for the a given system. So this is the basic request where we are gonna solve for this particular second order system. So to do that, we have a series of steps. So let me tell you, the first thing, solution. We have three steps to compute this, to generalize and to give a conclusion for this particular system equation. We have three steps. Step one, we have find out the singularity of system. Singularity of system. This is the very first step. The second point or step two is just find out the classify those singular points. In here, we have to find out the singularity of the system, and then after we have to classify singular points. So classifying the singular points. In final step three, based upon the above step one and step two procedure, we have to draw a phase portrait diagram. Phase portrait diagram for this particular nonlinear system. By the way, as an engineer, we have to know about why we are solving such kind of nonlinear system. Why? Why we are solving this? We have to answer this question as an engineer because this is a numerics value. This is a mathematics. So simply just computing that value it is a valueless for us. It's a meaningless. So we have to give a definition for every numerical analysis when we are faced in every phenomena. So the first reason is just such kind of system is not known, whether it is stable system or unstable system. Suppose this is a Vanderpool equation, what I mentioned in the sliding mode controller, or in this phase trajectory, or a given noun equation, noun system in this nonlinear. So if the system is like this, our target is that system is stable or not. That system is stable. If it is stable, it's okay. For controlling mechanism, we don't go further direction in order to stabilize a given system. So to check whether the system is stable, unstable, or saddle, we have to compute that system. And finally, we give the phase, the trajectory, which makes the system operable in a given particular point. So that's why we are gonna compute such kind of nonlinear second order system. So let's start from step one. So and step one, we are drawing to this point. So the step one said that finding out the singularity of the system here. So the singularity of the system means x1 dot is equivalent to 0, which means that if x1 dot is equivalent to 0, x2 is x no no, which is x2 is equivalent to 0. If x2 is 0, in the second point x2 dot is again 0, which means that we have x1 is 0, x2 is 0 in here. So x2 is 0 here, minus 2x1 minus x1 square minus 0.5 x2 is equivalent to 0. Here x2 is 0, x2 is 0. We have to insert the value in here if that is so. So our x2 is 0. If x2 is 0, we have to insert the value of x2 0 in here. So now minus 2 x1 minus x1 square minus 0.5 into 0, look into 0 is equivalent to 0. So this thing is goes to 0 now here. So I have minus 2 x1 minus x1 square is equivalent to 0. So from here I have x1 into minus 2 minus x is equivalent to 0. From here I have x1 is equivalent to 0, and this is x1, this is x1. x1 is equivalent to minus 2, minus 2. So from this particular point we need to find out our equilibrium point, is our singularity point. So our singularity point is x1 at 0 0. The first point is x is operated at 0 0, which is our point 1, and point 2 is here 0 and minus 2, or minus 2 or 0, minus 2 and 0. So these 2 points are our singularity points. So this is our singularity point. So based upon here, we have to go step 2. So in step 2, find the singularity for this particular system. Now this is our point 1 and point 2. This is so-called singularity of system that makes our system 0. Singularity of a system means that which makes our system is equal to 0, so this makes our system equivalent to 0. So so now we have a 0 0, and we have a 0 minus 2. These are the points in step 1. So later goes to step 2. In step 2 we need to find out the classifying the singular points. So in order to classify the singular point, we have to use the so-called Jacobian matrix. Jacobian matrix. Jacobian matrix is J of x dot is equivalent to A times x, A times this epsilon. So we have to find out this A. What is A? A is our matrix, which may be 2 by 2 matrix, or which may be 3 by 3 matrix. So we have to find out this A. So how we find out this A? So for that case, we have to assume our function f1 f1 into x1 x2 is equivalent to x2, and f2 x1 x2 is equivalent to this equation, which is minus 2x1 minus x1 square minus 0.5x2. So from here we have so-called lambda partial derivative of f1 with respect to partial of x1, partial of this f1, partial of f1 with respect to x2, partial of f2 with respect to x1, partial of f2 with respect to partial of what, x2 x1. This is our A matrix. This is so-called our A matrix. So f1 is from here, our f1 is here. So we have to compute in such a way, and then after partial of f1 with respect to x1 is 0, because we don't have x1 in this particular function here. We don't have x1, we have only x2, so this is 0. And what about x2? x2 with respect to x2, you have 1 here. Again, in the second equation in here, we have x1, 1 minus 1 minus of something else is, minus 2 here, minus 2 minus 2x1, minus 2 minus 2x1, because we differentiate this equation with respect to, first with respect to partial of x1, and then after we differentiate with a partial of x2. When x1 x2 goes to 0, in x2 we cancel out x1 in a partial differential case. So for that case, when we take the second x2 case, x1, all x1 goes to 0, and x1 0.5, x2 with respect to x2 is 0.5 only, which is negative 0.5. So this is our A matrix. Look, this is our A matrix. If that is so, our Jacobian is that, and then after we have to able to compute the form. So the form delta x dot is equivalent to A delta. So our A is in here 0, 1, minus 2, minus 2x1, minus 0.5 delta. So now I have to operate the lambda value at a given point, which is lambda x. This is lambda x. So now I have to operate in two cases. Case one, case one, uh, uh, case one, lambda I minus a, the absolute value of lambda a, I mean, which is a determinant. So the determinant of lambda I at 0, 0. This is case one. And the case two, because we have 2 points here, 0, 0 and minus 2. In case two, we have lambda minus I times minus a at operating at a point 0, comma minus 2. So in both cases, we find out for 0, 0, we got for 0, 0 case, we find lambda 2 minus 1. So for this case, we have to insert it because it is a long, and we got a sum equation in here. And for case 2, we got a sum equation in here. So For dot all, again we find out lambda 1 and lambda 2, lambda 2. So in this case, our lambda 1 and the lambda 2 from the given equation is, so for the first case, our lambda is a negative. For this case, our lambda 1 is in a alpha plus beta j. So this lambda 1 is a negative region. So if it is negative, the system makes it stable, which is case 2. In the second case, we substitute the value of this in the Uyghur. Lambda 1 is equivalent to lambda 1 is equivalent to 1.19, and the lambda 2 is equivalent to negative 1.69. Look, previously, if we have a negative lambda, we have a negative lambda. For this case, it is a negative lambda. Negative, negative lambda. Look here. For this case, which is a negative lambda, and for second case, we have a one positive and one negative lambda here. So in such case, we need to compute the step 3. The step 3 is, this is step 1, I mean step 2, this is step 2. In step 3, we are able to compute the phase portrait diagram. So the phase portrait looks like this. So I have here x1 and here I have x2. X2, look here. So for the first case, our real lambda is negative. Just check by your own self, which comes negative here. So for the negative lambda, value, the system is starting from somewhere there, and which is gonna merge or gonna diverge to the origin. Look here. Here, the system is starting from here, and which is diverges to the origin. So which, let's say, which is x0. So which starts from here and which came because of the lambda value. We have no any other argument to identify or to check the direction or to make sure in the direction. But the only guarantees is knowing and looking the value of the eigen value. The eigen value directs for our phase portrait diagram. Mind you, don't forget it. Just find it in substituting at x is equals to 0, 0. We got the negative lambda value. That negative lambda value phase portrait diagram is like this, because which starts in somewhere and which converges to the origin. When in the second case, when you come to the second case, in a case 2, look here, our lambda value, the second lambda, because it is elementary mathematics, I left all of you in such a case. So in the second case, we have a lambda 1 is 1 positive and 1 negative. If the case is 1 negative, 1 a positive, we said in a previous introductory class, if we have lambda 1 and lambda 2, the one lambda is positive and the other lambda is negative, our phase portrait phase makes a saddle point. So in this case, we have here the negative value, negative, here we have a positive and here we have a negative. So if this is a point which is a phase portrait diagram is like to be like this, which is uh, the phase portrait diagram, which is a phase portrait diagram. So this is a phase portrait. So for this particular system, our system is stable, partially stable. No, it's partially stable focus, and in the other point, our system is a saddle point. So this is why we are computing this particular system in such a way. And finally, this is a phase portrait diagram or the phase portrait plot. So thank you for being with me. Don't forget for some control work problems and also another related posts. Don't forget like, share and subscribe. See you until the next time. Bye bye.